So today I'm just going to be going through some practice problems to help you get some computation practice in before our next exam next week that you can expect to look quite similar to the second exam that happened online. So the content we covered for this exam, thankfully not a whole ton of stuff we covered in this last unit, but we've got some pretty big concepts. So linear regression. So for linear regression, you're going to need to know how to compute and interpret your linear regression. So you're going to need to be able to compute your regression equation and standard error of the estimate. So that's what we're going to be practicing today. Conceptually, you're going to want to understand the difference between regular linear regression and multiple regression, as well as think through conceptually what is mediation and be able to come up with an example of a mediation. And critically, focusing on mediation versus moderation. So not getting the two confused. I know they can be quite confusing. Once you get the difference down, you tend not to forget, but differentiating the two can be difficult. You'll be expected to understand mediation for this exam. So then for t-tests, you're going to want to be able to compute your different kinds of t-tests. So we're going to cover an independent samples t-test as well as a related samples t-test today. So you're going to want to understand when the two kinds of tests are appropriate, the different kinds of designs that lend themselves to one t-test analysis versus the other. And we're going to be practicing computing our different kinds of t-tests today. So like I mentioned, the difference between moderation and mediation is going to be key here. So we learned about moderation last unit when we were talking about complex correlation. So critically, if you're talking moderation, it's about thinking of a third variable that changes the relationship between your first two variables. So for example, there might be research indicating that there's a relationship between alcohol consumption and aggression, right? It might be the case that there is a positive correlation between alcohol consumption and aggression. There might be a third variable, though, of insult, right, provocation, that strengthens the relationship between alcohol and aggression, right? So this third variable of insult would change the nature of that underlying relationship between alcohol and aggression by, in this case, exacerbating it. This example we've seen before, right? You might have a example in which depression and stress are positively related, but the presence of social support buffers or diminishes that relationship, right? As you can see depicted here, those with a high level of social support, right? They have people that they can turn to when they're feeling down. The idea is that there's a relationship between depression and stress that is weaker when someone has a high level of social support. Okay, so again and again, moderation is when you have a third variable that changes something about the relationship between your first two variables. Okay, so all of those are examples of moderation. Mediation, on the other hand, is what we learned about when we covered multiple regression. So whereas all of those previous graphics showed a changing relationship between your first two variables depending on level of the moderator, mediation is when you're predicting a third variable explains why there is a correlation between your first two variables. So the graphics you're going to want to create are going to be these triangular formations, right? Where those two variables on the bottom, that math ability to interest in the math major, right? That's a relationship that you might seek to explain by coming up with a go-between variable, a mechanism. The idea here is that math ability boosts your self-efficacy in math, the belief that you can do it, which then in turn more proximally predicts interest in the math major. Okay, so if you're thinking of an example of mediation, put it into terms of a third variable that helps explain why your first two variables are related. Not changes how, that explains why. The graphic you're going to want to create to go along with it is going to be this triangular looking formation. Okay, so that's moderation versus mediation. So now on to our example computation. So first we're going to start with linear regression. So creating your regression equation and computing your standard error of the estimate. Okay, so what I would encourage you to do is once I explain the problem, pause this video, give yourself some time to work on it. I would say at least 10 minutes per computation. Okay, so we're going to start with computing your regression equation. So use this example data in which 6 participants have a authenticity score and a happiness score. Generate the regression equation that would help you generate predictions. Okay, so in this case, use authenticity to predict happiness. Okay, so your x versus y variable. So use this data to create your regression equation. You've got your formula for slope, your formula for y-intercept. Do those computations and then construct your regression equation. So again, pause this video, give yourself about 10 minutes to work on this computation, and then come back and we can see how you would complete this computation. All right, picking back up, we're going to walk through how you would complete this computation. So the first approach is going to be to compute your slope. So the formula for slope, which obviously you'll have on the exam, right? A lot of the pieces of this equation look quite similar to what you've done before when you computed your Pearson's R, right? So summing up your x, summing up your y, creating your xy terms and summing those up, your x squared terms, and then summing those up. So whereas for your Pearson's R, you also needed that y squared column, you don't need that. You just need to sum up your x values, sum up your y, sum up your xy, and sum up your x squared. So those are the 4 terms you need to compute your slope. So then this would be what your unsolved slope computation looks like. You just solve it down, simplify until you have your completed slope value. So this is the first piece of your regression equation. You're going to turn around and use that to compute your y-intercept. So to compute your y-intercept, you need your slope and you need the mean of your variable y and the mean of your variable x. So if you don't have that already, you would need to compute that. Pretty easy to do since you already summed up all of your x values and your y values. So then you compute your y-intercept and you have the second piece that you need to put together your regression equation. Okay, so this would be your completed regression equation that would then allow you to generate your predicted values for your y variable. Again, this would be what your key output in your SPSS analysis would look like. The regression equation components are available at the bottom in the coefficients part of the output. The actual values for your slope and y-intercept are to the left in your unstandardized coefficients in the B column. So that top value in the row labeled constant, that's your y-intercept. The value in that same column next to the x variable is your slope. So now you would be able to predict the happiness score given an authenticity score, even if that authenticity score didn't appear in the data set. So if you were asked to generate these predictions, right, it would be pretty straightforward. The idea is if you were asked to generate a prediction for a series of hypothetical authenticity scores, all you would need to do is plug those hypothetical scores in where the x is in your now completed regression equation and solve for y predicted. So it'd be pretty straightforward, the actual computation. You would just generate your y predicted values for your given x values. So then lastly for linear regression, moving on to your standard error of the estimate. So using the same data, you would need to determine your standard error of the estimate using this equation, which again you'll have available for you in the exam. So again, I would encourage you to pause this video, take about 10 minutes to work on the standard error of the estimate computation, and then come back to the video and see how the computation would be completed. All right, now on to the completion of your standard error of the estimate. Okay, so the part about computing standard error of the estimate that you need to make sure you don't neglect to do, because otherwise, how would you complete the formula? The idea is that you need to generate all of your y predicted values using the real x values that appeared in your data set. The idea is that the y predicted values based on your actual values of x are going to differ from the actual y values that appeared. The standard error of the estimate is going to be that average distance of y from y predicted. So basically, you're going to need to go through to all of the lines representing all 6 of your participants and generate a y predicted for all 6 of those individuals. And it's going to differ from the actual y score a little bit, assuming you do not have a perfect correlation between these 2 variables. So you go through and you calculate y predicted for participants 1 through 6. So y predicted for participant 1, participant 2, so on and so forth. You're just using that regression equation that you created, and you're solving for y predicted given all of those values of x. So then we're going to determine the standard error of the estimate by calculating the average distance of y to y predicted. Right? So we've got our x values, our y values, and then you just computed all of your y predicted values. So the next step is to get the difference between y and y predicted. Now here's where this is conceptually similar to when we used to compute our standard deviation. If you just sum up all of the values of y minus y predicted, they should add up to 0. The idea is that there's numerical balance of data points above your best fit line and below your best fit line. Some of those y predicted values are going to be higher than their actual y score, and some are going to be lower. There is numerical balance on the top side and below your best fit line. So what this means practically is that if you were to just add up all of your y minus y predicted scores, it will add up to 0 every time, even when there are discrepancies between y and y predicted. So for the same reason that you need to square all of your deviations to get your standard deviation, you need to square all of your y to y predicted values. Okay, so once you do that, then you add up the total of that column. This is going to yield a value for you that the magnitude is actually going to tell you something about the average discrepancy of y to y predicted. Okay, so just summing up y minus y predicted is going to be 0 every time, and it's not going to be useful for actually telling you the amount of deviation of y to y predicted. So you need to square those y minus y predicted values. So don't neglect to do this part, or else the numerator of your standard error of the estimate equation is going to be 0, and it's not going to work. So then from there, the actual computation is quite easy. You just need to plug that value you computed on the previous slide into the equation, and then from there, the actual completion is pretty easy. You can check the standard error of the estimate computation in your linear regression output in the model summary part of the analysis. So you can see there in the model summary part, standard error of the estimate is over there to the right. Okay, so being off by a few hundredths of a place, that's completely fine. Again, I would encourage you to round in your regression analyses to 3 decimal places. Okay, so moving on to your t-tests. As we learned, there's different kinds of t-tests that are appropriate for different kinds of data, and so we'll be covering both of the kinds of t-tests right here today. So first, we're going to start with our independent samples t-test. So this is going to be a research paradigm in which you have completely separate groups in your 2 groups, right? Participants are only receiving one condition or one level of your independent variable. So the people in your 2 groups are completely separate. So let's say I'm interested in the effect of mortality salience or making people think about their own death. Okay, classic terror management paradigm of asking people to reflect on their own mortality or a control condition that's equally aversive but not mortality relevant. And let's say I'm investigating the classic terror management hypothesis that thinking about your own death might provoke a sense of anxiety. So let's say I recruited 12 people and randomly assigned them to either think about mortality or think about physical pain. And then their values there represent their level of anxiety after the treatment condition. Okay, so your mortality group, the 6 individuals in the mortality group, are completely separate from those 6 individuals in your pain group. So take the data and compute your obtained t-statistic by comparing the 2 groups. Summarize the results and evaluate for significance. Okay, so here's all of the information you would need to compute your t. So you've got your equation for independent samples t-test. And then I've got some SPSS output showing the mean and standard deviation. That should be all the information you need to complete your independent samples t-test. So again, pause this video here, take 5 to 10 minutes, probably more towards the 10-minute side. For the independent samples t-test, go ahead and do that computation and evaluate your results. Okay, so coming back now, let's walk through how you would calculate your obtained t for your independent samples. Okay, so do recall that the variance is used in your independent samples t-test. Okay, so make sure that you don't just use the standard deviation. If you're given the standard deviation, make sure that you square it to get your variance, s squared. Okay, so you need your variance for your two groups separately, right? So the variance for your mortality group, the variance for your pain group. Easily accomplished by just squaring your standard deviation. You're going to need the mean for your mortality group and the mean for your pain group. And you need to know the sample size in your two groups, right? There were 12 overall, randomly assigned to the two groups, so 6 per condition. So then this would be what your unsolved t statistic would look like. So then from there, you simplify and solve down until you have your obtained t. Okay, so this is your obtained t that you then evaluate for significance. So to do that, you then turn to your critical t table. You find the degrees of freedom, directing your attention to the proper degrees of freedom row. Right, t-test for independent samples should be n minus 2. And then you find the column representing your critical probability value. So evaluating whether you used a directional or non-directional hypothesis, okay, that would get you in the one-tailed versus two-tailed row. Then you just go to the p equals 0.05 column, okay? So if you had used a two-tailed hypothesis and thus necessitating a two-tailed test and you wanted to use p equals 0.05, right, your critical t value is 2.228. Okay, so if you were using a one-tailed prediction or a directional prediction, right, maybe you had hypothesized that specifically you are predicting the mortality group will have more anxiety, not willing to accept as significant that the mortality group would be higher or lower, right? You could use a one-tailed test for significance. So the application of the decision rule, right, that obtained t of 1.127 does not exceed the critical t value, neither one-tailed nor two-tailed. So in this case, we would not be able to reject the null hypothesis. It does not appear to be the case that mortality salience versus pain salience differentially impacts level of anxiety. So that would be your interpretation. This would be your output for your t-test and SPSS. Again, you would look to the independent samples t-test part of the output. The t there represents your obtained t. Additionally, you have your degrees of freedom and your significance value. So with a p of 0.286, we cannot declare that this relationship between mortality and anxiety is significant. So moving on to our related samples t-test. Let's say I want to change my mortality salience paradigm by doing a repeated measures kind of an approach. So this would be a case where my participants are giving me multiple values, and I'm wanting to evaluate pre-treatment scores to post-treatment scores. So what makes this a related sample is that participants are being compared to themselves, right? So I can't disentangle the score of one individual pretest to post-test. The idea is people are being evaluated against themselves. So this would make the related samples t-test appropriate. So let's say my new mortality salience paradigm is I take a pre-test anxiety score, then I have my participants watch the horror movie 7, and then I take a post-treatment anxiety score. So in this case, you would compare the before to the after scores by computing a t-test for related samples. But once again, once you compute the t, you want to evaluate for significance and summarize your results. So here would be that data, right? Those 6 lines represent my 6 participants. Okay, so each row represents a participant's pre-treatment score, so before the movie, and then post indicating their post-movie anxiety score. So go ahead and pause this video. Take 5 to 10 minutes to compute your t for related samples, evaluate for significance, and interpret, and then return to the video to see how you would complete this computation. Okay, so moving on to the completion of your t-test for related samples. To do this, right, the idea of the repeated measures t-test is that I'm comparing everyone to themselves. So the idea is that the t is going to be the product of the magnitude of the difference score. So the idea being that I'm expecting some difference pre-test to post-test. So in order to do this, you take your data and you create a difference score. So basically, every participant's pre minus post score. Or you can do post minus pre. Doesn't matter the order with which you do the subtraction for your difference score. Flipping the order of the way that you're subtracting, it would flip the sign from positive to negative for your t-statistic, but the absolute value of your t-statistic would remain unchanged, so it really doesn't matter if you're subtracting post from pre or vice versa. So get your difference scores, and then square all your difference scores. Then you add up the total of your difference scores and the total of your squared difference scores. Then from there, you complete your t computation with those values, yielding a t of 2.21. So this is my obtained t that I now evaluate for significance. Okay, so I find my degrees of freedom rho. Again, recall that with your repeated measures t-test, degrees of freedom is n minus 1. Okay, so we had 6 participants, minus 1. So you direct your attention to that degrees of freedom of 5 row, and then you navigate over to the column representing your level of your critical probability value. So again, one-tailed versus two-tailed approach, this would be the result of what sort of a hypothesis you were using. So when appropriate, use one-tailed, or you can just always err on the side of using two-tailed. It never hurts to use the slightly stricter, more conservative cutoff, setting a slightly higher bar for yourself to clear in evaluating for significance. Okay? So then from there, you see the t-statistic is correct, the 2.21. Again, the sign of the t-statistic doesn't actually matter. That's just a product of how you ordered the subtraction to create your difference scores, right? So subtracting pre from post or vice versa. That would flip the sign of your t-statistic, but the sign doesn't really matter. You could go back and you could eyeball your means just as easily to figure out which group was higher and which group was lower. So the t-statistic is correct because the absolute value is correct. Okay, you can see that that particular obtained t is non-significant using the two-tailed approach. If you wanted to use your SPSS output to figure out the one-tailed significance value, SPSS does not give you the option to do this, but you can very easily do this just by dividing your two-tailed significance in half. So this is actually one of those cases where one-tailed versus two-tailed is the difference in terms of reaching significance. So in this case, if you had used a directional prediction and wanted to use a one-tailed test, you would technically have met the bar for significance. So the interpretation does depend on whether you were using a one-tailed or a two-tailed approach, because it is significant with one-tailed, but not with the two-tailed approach. So that'll do it for these practice problems. Let me know if you have any questions, and I'll talk to you guys soon.